let's continue talking about activities of non-volatile solids. Remember we said last time, if you have a volatile component of your mixture, then the activity is just going to be its vapor pressure over the mixture over its pure vapor pressure, right? So no problem with volatile components of a mixture. So you can have a solute. If it's volatile, you can use Henry's law, okay, or you can use Raoult's law to get its activity. But whenever you have a non-volatile solute, then you don't have a vapor pressure. So what do? You have to resort to Gibbs-Duhem equation. By monitoring the activity of the solvent, the volatile component, you can figure out the activity of the solute, which may or may not be non-volatile. Okay, and we illustrated that in the previous PowerPoint in the previous lecture. So anyway, the idea here is this. Okay, I gave you this is the example I gave you. Basically, you can figure out the natural log of the activity coefficient of the solute using the Gibbs-Duhem equation. Is just equal d of ln gamma 2 will just be minus x1 over 1 minus x1, where x1 is the mole fraction of your solvent, d ln gamma 1. So you need to be able to have to monitor ln gamma 1 versus mole fraction of component 1. Okay. Let's see. Yeah, or you can rewrite this. I think in the original video, I think I might have this as x2 over 1 minus x2 over x2. Okay, so you can also rewrite this as, instead of x1, you can write 1 minus x2, since x1 plus x2 just add up to 1. Over, instead of 1 minus x1, you have x2 there. So if you have ln gamma versus x2, okay, then this, you can integrate both sides. This integrates to ln of gamma 2, okay, would be equal to minus integral of x2 over 1 minus x2 over x2 d ln of gamma 1. And if you can monitor ln gamma 1 versus x2, you take d ln gamma 1 dx2 dx2. That basically is the same formula right there. So you integrate this from x2 equals 0 to whatever x2 you're interested in. Okay. Now in the video where I showed you the example of this, that was kind of lengthy with the math kind of stuff. The problem we noticed was that this integration is kind of hard to do because of this x2 down here. Okay. So when you do your plot, you go to negative infinity in your plot, and when you integrate, you can't get. You're gonna have a problem with that integration. So a more practical method, okay, in the slide that I seems to have forgotten, and I skipped from that previous lecture, is this slide right here. This is using practical osmotic coefficients. Okay. So using practical osmotic coefficient is a lot easier. So let's first define what a practical osmotic coefficient means. Okay. This definition of practical osmotic coefficient, phi, is equal to ln Pa star over Pa times 1 over molar mass of the solvent. Nu is the number of particles that your solute can generate in water. So nu m is actually the total solute molality. Okay. This is the total molality of solutes. And Pa star over Pa is really nothing more than the activity of your solvent. Okay? Oh yeah, that's 1 over the activity. So if you want that to be Pa over Pa star, you'd have to put a minus in front. Okay? So let me go back. Let me go to the set up that definition first. Let's see where that comes from. Okay. First of all, let's start with our definition of the activity of your solvent. ln A. Let's call our solvent A. Okay. Activity of A. All right. Now, in a very, very dilute solution, almost pure A, then activity of A, if you recall, using Raoult's law, is just mole fraction of A, right? And mole fraction of A is just 1 minus mole fraction of the solute particle, so 1 minus XB. Okay? Now, if XB is very, very small, then that's approximately equal to negative XB. So ln of 1, this is a very common approximation we use. When you're dealing with very small x, ln of 1 minus x is approximately equal to negative x. Okay? So if that is the case, you can then say that ln of activity of A is approximately equal to, okay, negative xb, where xb is the mole fraction of B. So in very dilute solution, what's the general definition of mole fraction? It's moles of B over moles total, right? And A plus NB. And then you have to put a negative there. But if you're dealing with a very dilute solution, what is this NB compared to N sub A? Very small. So again, we make one more approximation here. It's going to be negative NB over N sub A. Now we're going to express this in terms of molality, because molality is moles of solute per kilogram of solvent, right? So if you have 1,000 grams of A divided by the molar mass of A in grams per mole, okay, this will give you the number of moles of A, right? So the number of moles of A is just 1,000 over molar mass of A. And number of moles of B, if you have 1,000 grams of A, then the number of moles of B will just be the molality. Okay? Right? Molality is moles per kilogram of solvent. So we're just going to call that M. So this is going to be equal to M, negative M over 1,000 over molar mass of A. So that's going to be negative M times molar mass of A over 1,000. Okay? So let's continue with that. So we say ln of activity of A is approximately equal to negative molality. We're just going to use numerical values here because mole fraction should really be a unitless quantity. This thing is going to be unitless. And if you plug in units for molality and molar mass, you're going to get confused. Okay, just keep in mind that when we're doing this, if we're using a numerical values of molality in moles per kilogram and molar mass in grams per mole, and you have 1,000 there, you don't put any units there, the answer should come out unitless. Okay, so this is going to be molality times molar mass of the solvent A over 1,000. Okay, that's natural log of activity of A, approximate value. That's true at very dilute solutions. So we're not going to use, again, the typical strategy we've been using all throughout the course. Every time you have a simple, you can create a simple scenario with a simple formula. What you do is you can extend it to other cases by introducing a correction factor, right? So we're going to say that is only true at this is going to be equal only at very low concentrations. So if we get into higher concentrations, okay, less dilute solutions, then we have to apply a correction factor. This is where we introduce. So now to make this thing equal, we're going to introduce a correction factor, phi. So this phi right here is your osmotic coefficient. It's called the practical osmotic coefficient. Okay, so phi then is equal to, what is it? 1,000 over molality times molar mass of A, and there's a negative there, natural log activity of A. Okay, and this is going to be negative 1,000 over total molality of solid particles, molar mass of A, natural log of what is the activity of A? PA over PA star. Okay? Or if you flip that, that becomes PA star over PA 1,000 1000 over molality times m sub a, that becomes a plus. And that's what we had in the formula earlier. Okay? So this is the formula we have up here. Okay, and you might be asking, where did the 1000 go? Okay, the textbook I copied this from, the molar mass is given in kilograms per mole. So if you don't put a 1000 up there, then this would have to be in kilograms per mole. Okay, and what is this new thing doing here? For example, if you have sodium chloride, in very dilute solutions, what do you get? You get sodium and chloride. So you actually have to multiply your molality by 2. So in that formula I gave you earlier, that M stands for the total molality. If you want to explicitly account for the possibility of ionic solutes, then you have to put that new right there. In fact, this particular method is going to be very useful for ionic solutes. Okay, and the reason for that is given here. Your activity of the solvent doesn't vary much. It's very close to 1. Okay, and so you can get more reliable results if you monitor the osmotic coefficient, which varies a little bit more than the activity coefficient itself. So it's more sensitive to changes in the activity of the solute. Okay, so A is your solvent here, B is your solute, nu is total particles per formula unit, M is molality. So this is what our phi is, okay? What our phi is. And so the expression that we use is actually, I derived is 1000. If you use grams per mole for molar mass, so it's going to be 1000 over molar mass times the total molality times ln of activity of A, which is PA over PA star, and you have to put a minus. So that's the same thing, okay? If your molar mass here is in grams per mole. If you want molar mass in kilograms per mole, then you have to use this formula. And notice your PA star and PA are flipped. That just affects the sign in front of your expression. The practical osmotic coefficient is going to be a number that is going to be positive. Okay. Yeah, it's positive. Because ln of PA over PA star, this is going to be a negative number. So that's negative, negative, that's comes out positive. Alright, so if you know if you can calculate the practical osmotic coefficient, okay, then what you can do is you can apply the Gibbs-Duhem equation and you can figure out this formula right here, ln of gamma of your solute, so activity coefficient of your solute, which depends on its molality, is just equal to its osmotic coefficient at that molality minus 1 plus this integral right here, phi minus 1 over m dm from m equals 0 to m equal to whatever molality you're interested in. So let's see where that comes from in terms of the Gibbs-Duhem equation. Okay, so let's continue down here. Your Gibbs-Duhem equation says N1, N sub A, N sub A times D of ln A, activity of A, plus N sub B times the differential of natural log of activity of B must be equal to 0. So let's start with that. Okay. And so we're going to assume you have a kilogram of solvent. So what's our N sub A again? This is 1000 grams divided by the molar mass of A, right? So you have D ln A, activity of A, plus number of moles of B would be our molality, right? If there are 1000 grams, the number of solvent, then the number of moles of solvent would be M, D ln activity of B equal to 0. Alright, what's ln of A, activity of A, using practical osmotic coefficient? Right here. ln activity of A is what? Is minus, you can rearrange this, m sub A, phi over 1000, right? Just rearranging this equation over here. Correct? Multiply both sides by molality, molar mass of A divided by 1,000. That's ln phase of A. So I'm going to say this is 1,000 over molar mass of A, differential of, instead of ln A here, what do I write? Minus M times molar mass of A over 1,000 times phi. Okay? Plus, that's our activity of B. That's just gamma B times the molality, right? Activity of B is just the molality of B. If it's ideal, you multiply it by gamma. If it's not ideal, so this is going to be equal to 0. Alright, let's simplify. I can factor out these constants, and what happens when I factor them out? M sub A cancels, 1,000 cancels, right? So this is a minus D of M phi. M and phi are both variables, they depend on the molality, plus M times the derivative of ln of gamma M, so the differential. What is ln of gamma? Ln of a product is the sum of the logs, right? So this is ln gamma B plus ln of M equal to 0. Alright, so what is this right here? Let's simplify this one. This gives, so I'm going to keep this minus d m phi plus, this is m d of ln gamma B plus d of ln M equal to 0. Okay? The differential of a sum is just the sum of the differentials. And the reason I'm doing this is I want to solve for this. Okay, so what do I get now? I need to solve for this, so let's solve for that. D of ln gamma B equals 1. I'm going to move the ones that I don't want on the left side to the right, so that's plus D of M phi. And then minus M times D, I have to multiply those two, right? Minus M times D of ln of M. So that's my expression for D ln gamma B. Divide both sides by M, right? Okay. So what is the differential of a product? Let's look at this first one right here. That's M times D phi plus phi times dm over M, right? Minus M cancels here. What is D of ln M? It's just dm over M, right? The differential of ln x is dx over x. So can we simplify? What we have here is just your M cancels out over here, so it's just d phi plus phi over M dm, right? It's phi over M dm, this is d phi, minus dm over M. So I can rewrite this as d phi. I can combine the two dm's, these two, okay? So d phi plus phi over M minus 1 over M dm, which can simplify further into d phi plus phi minus 1 over M dm. So that is your D of ln of gamma B. Alright, so what happens if we integrate both sides? This is going to be ln of gamma B equals integral of phi evaluated from M equals 0 to whatever M you're interested in, right? And integral of this, phi minus 1 over M dm from M equals 0 to whatever M you're interested in. Since I'm using M as my limit here, I'm going to put just prime there. Okay. This is, you don't want your integration variable and your limit to be the same. So this, so that's going to be phi minus 1 over m dm. Alright, so what happens here? What's phi? This is going to be phi at m minus phi at 0, right? Plus this integral right here, phi minus 1 over m prime dm prime from 0 to m. What is phi at 0? At phi at 0 molality means pure solvent, right? Pure A. What's the osmotic coefficient for pure A? Remember, in very dilute solution, this correction factor that we introduced, this correction factor is going to be 1 in very dilute solutions, right? So in pure A, it becomes 1. So phi at 0 is equal to 1. So this becomes phi of m minus 1 plus integral of phi of m minus 1 over m dm from 0 to m. So that's the formula right there. Okay. The nice thing about this, you might be saying, okay, we could have trouble again integrating because that m in the denominator when m equals to 0 will go to infinity, right? And the whole will make the whole thing blow up. But what happens here is, if you can typically write phi as something like am. You can fit it to a polynomial, maybe a cubic or a square polynomial, for quadratic polynomial, for example. You can say am cubed plus bm squared plus and so on. What's the last term right here? What should phi be when molality is 0? Should be 1, right? So when all the molalities are 0, then that phi should be 1. So that numerator should have a plus 1 there. So when you subtract the 1, so if you subtract the 1 from the numerator, minus 1, and then divide by m, the 1 cancels out, and this m will, the denominator will cancel out when you carry out the integration. So it's very easy to integrate. Okay, so there's the formula right there at the very top. Okay, ln of gamma at molality m is phi at molality m minus 1 plus the integral of phi minus 1 over m dm. So let's apply that now to the data for sucrose that I gave you in the handout. This is from McQuarrie's molecular physical chemistry and molecular approach. Okay, so we're just going to use the first. So let's do the data for sucrose, and we're only going to use up to molality of 1 to make things easier. Okay. So let me go ahead and bring up Excel. So let's enter those numbers. So we're going to enter molality here. And experimental vapor pressure of water, which is given in torr. So molality is 0, 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. This goes all the way to 6, but we're just going to stop at 1, okay, just for illustration purposes. And so let me go ahead and enter the vapor pressure. Vapor pressures are 23.756. 23.713, 23.669, 23.625, 23.580, 23.534. At 0.6, it's 23.488. At 0.7, it's 23.441. At 0.8, it's 23.393. At 0.9, it's 23.344. And at 1, it's 23.295. I'm going to pause the video here. I'll give you time to get caught up. Alright, so let's continue. So we have the vapor pressure of water. So how do we calculate the activity of water? What's the formula for the activity of solvent? PA over PA star, right? So what's our PA? Okay, let me make this bigger. What's our PA? PA is this one right here, right? What's our PA star?
Same one.
Same one, because that's pure water when you have molality of 0, right? So B3 over B3, that's 1. But if I want to copy that down to the rest of my column, what should I do? The denominator, PA star, I put $sign so that the B3 in the numerator will change, but the B3 in the denominator should stay so as B3. So edit it that way and then copy it down to the rest of the column. And those are your activities. And if you look at the table in your handout, you'll notice that it is those numbers, right? So that's how you get your activity of your water. How do you calculate now the osmotic coefficient phi? What's the formula for phi? Phi equals, oops.
What I just said.
1,000 on top. Negative 1,000 over molality times molar mass of A, natural log of the activity of A, right? So that's going to be molar mass of A. What's our A here? Water. What's the molar mass of water? 18.016 grams per mole. We're going to use 5 sig figs here. Okay. And we have our molality in column A. And so we have all the information we need. So let's do that. So this is going to be equals negative 1,000 divided by 1,000 divided by molality. Let me see. Negative 1,000 times, I'm just going to do ln of A first. ln of activity of A, which is that one, divided by the molality, which is that one, divided by molar mass of water is 18.016. And I can't get a number there. Why? Because I'm trying to divide by 0 molality. Okay, but you do know what should that number be? What's the limit of that expression? It should be 1, right? Because that's a correct, basically your correction factor. So it's not defined for 0 molality. So we're just going to say it's 1. But we can copy that formula to the rest of the column. Okay, so those are your numbers. But this phi should be 1 for 0 molality. Okay? The practical osmotic coefficient for the solvent should be 1 if it's pure. Okay, so, but we have this formula right here for the rest of it. So it's going to be, for molality equals 0.1, here's your formula. It's negative 1,000 times the natural log of the activity, which is in cell C4 here, divided by the molality, which is in A4, divided by the molar mass of water, which is 18.016. And you should get the same number in the book. You're not getting it?
The first one is supposed to be all three, right?
Okay, so let's continue. We got our practical osmotic coefficient. Now remember, if you have like a 1,1 electrolyte like sodium chloride, then this molality down here has to be multiplied by 2, okay? So you have to put nu there if you're dealing with electrolytes. But in this case, we're dealing with sucrose in water, so it's not going to give you more than 1 particle per molecule of sucrose. So after that, what do we do now? We need to calculate gamma. Okay. Actually, we can calculate ln gamma first. Gamma 2, gamma B. So how are we going to do that? What's our formula for ln of gamma? Okay. So ln of gamma b equals phi minus 1 plus the integral from 0 to m of phi minus 1 over m dm. So what we need to do is we're going to fit phi versus m to a polynomial. And so let's go ahead and do that graph. Okay. So insert a chart, scatter plot. We're going to plot, select data. Design, select data, remove, and then add. Okay, what do we want to do first? Phi versus m, right? So which one is phi? Okay, let me get rid of this first. Let me zoom out a little bit so I have a little bit more room. Okay. So what I'm going to do is select data. Okay, remove that one. Add a series. My x values would be molality, right? And my y values would be phi. And what do you notice there? That's almost a straight line, right? You'll have some curvature if you have if you go further out. Okay, so this is phi versus molality. So we can try to fit this to a polynomial. Okay, let's not do a straight line. Let's just do a quadratic polynomial, I think. And you'll notice that's a very good fit right there. Let's show the equation. Now we want to force our intercept to what? 1, right? So you force your intercept to 1 because phi at 0 molality should be equal to 1. Now if you don't have that option, if you can force your intercept to 0 only, I think in older versions of Excel, you might have to force your intercept just to 0, or when you're doing your regression, you can plot phi minus 1 instead versus molality, okay? And let's display our equation on the chart. And there's your equation right there. So we're just going to use this equation. So let's put a little more sig figs there. Format trend line label. Let's make it scientific notation. Let's say 5 decimal places. Just so we don't worry about round off errors. Okay? So those are our that's the polynomial fit. So you can do more than just 2 second order. You can go third order if you want. Okay, so our phi then we say is equal to am squared plus bm plus 1. Okay, so that's going to, what's our a here? Let me just capture those numbers. Okay, copy this number. This is my A. And my B. And my 1. No, well, I don't need to copy that one. Okay. So that's your phi versus molality. What do we do next? How do we calculate ln gamma? It's phi minus 1 plus this expression right here, right? So let's go back. Let's say, what if our phi is equal to am squared plus bm minus 1? What would this integral be? Phi minus 1 over 1 dm. What's integral of am squared plus bm minus 1 over m plus 1, okay? So that's your phi, right? That's your phi minus 1 dm. And like I said, we're going to make these primes because our limit is going to be from 0 to m. What would that be? That's going to be integral of am prime plus b, and then the 1 cancels out, right? Am dm prime from 0 to m. That's going to be equal to what? Am prime squared over 2 plus b m prime evaluated from 0 to m. Right? So it's going to be am squared over 2 plus bm minus 0 minus 0. Right? So that's your integral. So what is our ln of gamma b? Is equal to phi minus 1 plus this integral, which is am squared over 2 plus bm. And what was our phi? Am squared plus bm plus 1 minus 1 plus am squared over 2 plus bm. So can we simplify that? Select all terms that have m squared in them. So that's a plus a over 2. What's a plus a over 2? 3 halves a, m squared. Bm plus bm, that's 2bm. And then 1 cancels out, right? So that's your expression right there. Okay, let's verify that with MathCAD. MathCAD, where's MathCAD? So you need the integral. So you have a times m raised to the power 2 plus b times m plus 1. Okay, that's your phi. Right? Okay, and then minus 1, right? Plus the integral from 0 to m. And I'm going to call it, instead of calling it m prime, I'm just going to call it x. So it's going to be a times x squared plus b times x plus 1 minus 1, right? So it's just going to be b and then divide by x. So it's just going to be ax plus b dx. Okay, so evaluate that, simplify. It's 3 halves am squared plus 2bm. Okay, so that's our formula. So what can we do now? We can put the formula here for ln of gamma. What's our formula? Equal to phi minus 1 plus, what was it? 3am squared. Oh no, it's just 3 halves am squared plus 2bm. Okay, so this is just going to be equal to 3 halves times a. What's our a right here? This is our a times m squared, and our molality is over here, plus 2 times b, which is this one from our polynomial fit, times m, which is also this one. So that's your ln gamma b, and you can just copy that down. Oops, to copy that, I want my C8, my A and B addresses not to change. So I want my C18 and my C19 not to change. So $C, $18, $C, $19. Okay, let's copy that down. And let's put that in um, in regular format. What happened? Okay. Number, let's just say 4 decimal places. And you can see that should more or less match up with what you have. Okay, why do I have okay, that should be times. Okay. Huh? Okay. This is 3 halves am squared plus 2 times b times a3. That is the formula, right? Let me see. Let me pause this. Okay, so we got this thing fixed. So this is going to be 3 halves times a, which is C18, m squared, which is A3 squared, plus 2 times bm. And then we have to copy that down to the rest of the column. So it's 0 for the top one, right? And these are your numbers. Now, these are not going to be exactly the same as in the book, because what he did in the book is he went all the way to 6 molal, and then he, I think he went over like 5th order. So there's your gamma B, ln gamma B, and then the final step will just be gamma B. How do you get gamma B if you know ln gamma B?
Yeah.
Inverse log. E,
Yeah.
so exp of ln gamma. So of course a gamma B is going to be 1 for 0 molality, and you copy that down. These are your gamma B's. Okay, so that's how you figure it out. That's how you do practical osmotic coefficients. Okay?